Let's discuss question number 19 from test 1. Let's read the question. Thermal resistance of a wall with conductivity K, area A, thickness L and convective coefficient H is. Okay, so this is a question from heat transfer. I am writing it as HT. Okay, so what is asked is the thermal resistance of a wall and with conduction going on in the wall. So thickness L is given, the area of cross section on both sides is A, and there is convection on both sides represented by heat transfer coefficient H and ambient temperature T. Okay, so heat, let's say if you're inside the room, if it is hot and heat is flowing, T ambient 1 is more and T ambient 2 is less, so heat will basically flow in this direction. So there will be convection here, there will be conduction here because it's a solid thing, and then again there will be convection on the outer side. So now Fourier's law says, Fourier law represents heat conduction in a plane wall. So heat conduction in a plane wall is given as under steady flow K A, area of cross section, temperature difference across this by your thickness L. So this in the resistance form I can write as L by Ka, and this is your thermal resistance due to conduction. Okay, and now heat flow, so this is due to conduction. Now heat flow in convection is given by HA delta T, or let's say from here to here, so it will be T ambient 1 minus T1. So temperature is T1 here, here T2. Okay, this is the first. Now heat flow on the outer side, that is from T2 to V is HA. Now heat transfer coefficient is same throughout, so T2 is more minus T infinity 2. So this is heat flow through conduction in a plane wall, which is T1 minus T2 by R, and R is L by Ka. Heat flow through convection is given by this, and we have convection on both sides, so I have written this. So this also, each of this convection heat transfer we can express in terms of resistance. So we can express in terms of resistance, and even this also T2 minus T infinity 2 by 1 by HA. So we know that heat flow is same, it's a series network, so we can express H as Q is same, which is Q conduction, Q convection and Q convection 2. So first equation, okay, now this can be written as T infinity minus 1 by T1 by R convection 1, and this is R, this is T2 minus T infinity 2 R convection 2. So you have 1, you have 2 and you have 3. Now if we add 1 plus 2 plus 3, what we get is, okay, so I'm just adding this. So okay, or before adding, let's rewrite one. Q conduction into resistance of the conduction is T1 minus T2. Okay, let's not add, let's add it at the later stage, but first just take the resistance term on the left hand side is T infinity minus T1, and third equation becomes convection 2. Now if I add these three, so basically Q's being same because it's the amount of heat transferred goes only radial outwards, it's only outwards, so heat transfer through convection or heat transfer through conduction and heat transfer is same. There is no side heat change. So when you add this, Q is the total resistance conduction plus convection 2, and when you add this, T1 minus T2 plus, so what I get is T infinity 1 minus T infinity 2 and Q, and this is your total resistance, conduction plus convection plus R convection 2. Now these, if I, so this is basically something like your total temperature difference starting T infinity 1 and T infinity 2 by your net resistance. And so I can write the net resistance is R conduction, which is L by Ka, R convection, which is H by HA basically, or 1 by HA, because this is what we defined as R convection. So 1 by HA, and this is also 1 by HA. So this comes out to be L by Ka plus 2 by HA. The other way of saying is this is thermal resistance HA, this is conductive resistance L by Ka, and then you have another inverter resistance. So it's a series network with T infinity 1 here, infinity 2 here, and the heat flow SQ. So that is the meaning of this expression with net resistance given by this. So though you may answer it directly, but there was this much theory to explain this. So the answer or option is C. Thank you.